Good afternoon, everyone. First of all, I would like to thank you, Radaz and Unicamp, for this nice invitation. We've been working together for several years. I won't say how many, but for many years now. And it's really nice to see this event happening here because I was part of the beginning of this project. So there is a tiny part of my work in this SAR radar. I'm really proud of it. Now, actually, the destiny took me away from here, and now I'm working with SAR, leading a small team in the UAE. I will present the team later. And it's really interesting to see how this has grown in terms of applications, results. Really interesting to see all these results from other events or conferences I been part. So I will present here our efforts in the UAE. We have a strong partnership with Radaz. Actually, this partnership started when I went to the UAE 5 years ago, and it has grown stronger and stronger. So I will present to you here 4 use cases that we're doing there, from utility to archaeology, and what's coming, our challenges, etc. Okay. So before I start, I would just like to present the TII. What is this Technology Innovation Institute? It's an applied research center that was founded during COVID times, end of 2019, I believe. And it started with 5 centers, and Directed Energy Center was one of them, focused basically on direct energy, high power microwave. And of course, the whole thing, as they start hiring people, this changed a bit. So, for example, when I was hired, I presented this project specifically to the audience in the center, and they were really impressed by the results we had by the time. It was basically the results from the sugar cane. So they decided to start this partnership, and this thing has progressed. So the Technology Innovation Institute, or TII, is under this Advanced Technology Research Council that comprises 3 main branches, let's say. The TII, that is the applied research, so we provide solutions by developing by ourselves or joining with partners like Radaz. The Aspire, that bridges the gap between the industry, not only local, but we have also we have been working with in other countries in the region, and the technology they need. So everything that goes through for research goes under Aspire, and Venture One, that's the commercialization side. So if you have a solution that can be already commercialized, it goes Venture One. So this is the Advanced Technology Research Council, ATRC, and how this is organized under the government of Abu Dhabi. So for those don't know, we have several emirates there, and Abu Dhabi is one of them. Abu Dhabi is the one founding this research council and also TII, but for the whole emirates. So the Direct Energy Research Center comprises several areas. In our is the remote sensing and focus on SAR. And the team I have here just presenting our chief researcher, Dr. Felix Vega. Dr. Islam Yahi is the director. And the team is basically me, a local, Jahar Al-Hamadi, and 3 Brazilians. So as you see, the SAR team is basically Brazilian. Eduardo, most of you know Eduardo. Leonardo Beans. Leonardo was Juliana co-advisor in her PhD thesis. And Lucas is the new joiner, let's say, although it's been there for 8 months already. So have presented the center Of course, I want to tell you that we're using the drone SAR by Radaz. I want to mention also that this is a really lightweight system, less than 5 kg, that operates simultaneously in 3 bands, PLC, acquire data simultaneously, what is a huge advantage compared to other systems. But I won't present the system, of course, you know it quite well. I will focus on the applications. So we'll talk about the pipeline detection, water leakage detection, archaeology mapping. It's something we realized along this process we needed to improve the processing. So I will explain why and how we're trying to enhance the back projection, eliminating side lobes that affect not only the surface but also the subsurface image. So let's go. About pipeline, why this is important? One of the main questions we've been asking when we started these is, can you detect the pipelines? And they are really willing to map the whole UAE and know where are these pipelines. You could say, okay, but this is a new country, they should know, etc. What is not quite true. The country itself is 60 years old, quite new for a country, but they have several problems because there is no legacy, so they have no complete records about these pipelines. And since the construction is happening everywhere, to every area you look, you are seeing cranes. They need, and they at least to complete what they already have, or at least in GIS systems. So this is a really huge demand. And most of these lines, they are around the cities, of course, but also through the desert. And they need to know, because this is also related to the second use case I will present, the water leakage. So this was the question. And it's quite complicated because we didn't have ground truth to prove this. So we decided to build our own lab. I'm showing you here the area where we built this pipeline. So we are seeing here, we have 100 meters of plastic pipeline, 10 centimeters. It goes here, goes down here more 50 meters, and it splits into branches. And I will explain later why we are doing this way. So at the end, we have this plastic pipeline, this 20 centimeters diameter, buried around 1.5, 2 meters deep. So this is the idea. 2 valves there, because this setup was also designed for detect water leakage underground. So this is the site we built with certain, sorry, come back here. So here you see the full view from above. We have there, of course, a water tank, about 9,000 liters for the leakage detection. In this first part here, the pipe is 70 centimeters and goes down from this point there, from 70 to 1.5 meters, and then it splits into branches. Just to see, to show you here, how is the stratification? We have this gravel layer here in 2 different aspects in pure sand. Building this was complicated because the guys were digging and the sand was falling over, so, but they could do it. So this is the whole setup, and here's some more details. So this is the setup we are using. We used actually to try to show that we can detect a pipe underground. In this case, plastic. At the end, after everything was covered, this is the view. This is what we can see from the top or from the ground. This concrete box is there to contain the valves we use to leak water to one side or another one. And this is the final setup. on the surface, the pipe is the top of the pipe is 1.5 meters. Okay. And of course, we flew the system there. And after a while, and I will explain at the end of this talk what was the main challenge here. But after processing and reprocessing and applying deep learning-based segmentation and correlation, we could show that it is indeed possible to detect not only the planimetric distribution, but also the altimetric distribution. As you see, the blue lines are the shallower ones, around 70 centimeters, and the reddish one are around 1.5 meters. In this case, this was a work developed by Lucas. In this case here, we have some states. We are reprocessing this data based on what we've learned recently. But we could see, especially in this part, that the neural network operated quite well. This is around 1.5 meter, what was detected. From here, it's saying also 1.5 meter, and it can be considered because it goes from this point to that point in 60 meters only. So this slope is really mild. We could consider even planet. So this is, here of course the system got lost. I believe Lucas used this part of the pipeline to train the neural network, so more data of course is needed. But this is an interesting case. Another point here, we have a profile in depth ranging from 70 to 150 centimeters. And you can see here, it can be seen in a better way. The red lines are the field measurements. Before closing, we measure the depth in 3 points, and this is the red line. The green one, what Lucas did, because he split this branch in 9 parts, and for each one, he took the value measured by the neural network and interpolated. You see, of course, the system is not quite precise, but the deviation is really small. And here also another point that we plan to improve. The slices are, each slice is 1 meter apart. It's something we're improving because since we process this data, we can now use GPU, so the processing is much faster. In the blue light, he took a piecewise linear approach, which I don't like much. I prefer to show the green light because you see the neural network could indeed infer the depth with certain quality. So this is one of the applications. So for this site, the pipeline detection. This is something we are planning to revisit because the site is there available to us. So we'll fly again using different flight approaches, covering with more, improving coverage, let's say, because basically here we have a single flight. Now we plan to have more flights over the same area to improve the coverage, multiple angles. But this site was also used and was initially designed for detecting leakage, underground leakage, because this is, again, a trend in the UAE. Why? Well, obvious reasons. You see, it's a really dry country. I was talking during lunch about this. Basically, 9% of the water comes from desalination plants. So they desalinate the water and distribute all over the country. So you see it's a really expensive process, and the less you use, the better. And what they have there, this is part of why detecting also the pipelines are important, because much of this is distributed by old pipelines, only this. During summer, outside the temperatures on the surface can reach is 55 Celsius. Imagine underground. In these pipes, they work, they contract, they expand. And for these reasons, there is a lot of loss in water. So they are interested in mapping this. Where is leaking? How can we fix it? So one of the questions is, can you measure underground leakage? So, well, based on, we did this, this setup again. And here we have these three branches for to look differently in both sides. The first one, the yellow, the target area 2, is fully perforated, as you see there. And we look at area, if you want, all over the 40 meters in this branch. The other one, we try to make it more localized. So only here, 10 meters. And the results are going to show you are related to this side here. What we did, I will explain how we did. And of course, we have two valves there to control to where we are leaking all this water. So, so this was the experiment. We have this target area, 10 by 40. We are open only valve 1, and we are processing from surface up to 3 meters of depth. So the total volume of this target area is 1,200 cubic meters. I will explain why I consider this information important in a second. What was the process here? We flew once over the area to establish a baseline. We leaked about 2,000 liters of water, flew again, more water, flew again, more water. At the end, only 430 because this is what was left in the text. So this was the procedure. So see, it took from 10 a.m. to 12 p.m. So 2 hours under the sun of June. That's not really pleasant, but anyway. And the processing, this work here was done by Leonardo, but also the main work was done by Giancarlo and João. We have, as I mentioned, this partnership, and this is part of one of the packages Radaz is delivering. But we are working together in this, and it's based on our paper yet to be published about measuring soil moisture using 3 bands. So here what we have, the surface, we are using the 3, the L and C, and for underground, one can correct me later, we are using only P and L. And the whole methodology is here. And what we have at the end is this. I'm showing here this general view, but this is the surface plot. What is interesting is that once you have this volume underground, this reflects on the surface image. It's something that maybe we need to work on it in certain cases, and I'll explain later why. But you see here, the first leakage, the area was already humid, and this is based on initially the maximum reflectivity. The second one, so here 2,000 meters or 2 cubic meters, there 5 cubic meters, and there 5.4 cubic meters. So why is this important in my opinion? Because at the end, we are talking about a volume. We process this from 0 to 4, 3 meters deep. And we just leaked 5 cubic meters in the area of 1.2 1,200 cubic meters. So the system could indeed detect. It's true that we faced several issues here, and again, I will mention why this later. But here we have the plots, slice by slice. So you see here surface only, the baseline. So everything is related to the baseline. First, the leakage. The second one, and you see how the soil moisture, and since we didn't measure we didn't follow the whole process, meaning we didn't have ground truths there, only the amount of water we're leaking. So you can see these are qualitative results, not quantitative. We need to repeat this process, now going there, collecting the samples, several depths, and relating these to the reflectivity we have on the ground. But it is how, and this is enough for us when the client comes and asks, can you detect leakage? They are not interested how much you are detecting, only if you can detect it. So it's a result that is being really well received. So this is one case. Here, 1 meter deep, and you see again how the water spread. Yesterday I was talking to João about this because I have also a 3D plot of this I'm not showing. And what we see when we plot this 3D is like a cone. The whole water comes and start, of course, in spreading underground. We need collaboration with geologists because how the sand is absorbing the water is another point. But we see clearly here that the water occupies more surface here at the surface, so at least reflects this way than at 1 meter. But still can be seen that we have more water from the fourth flight. So this is one point. So these are the use cases for utility, for infrastructure. Probably the most trending one. This is what they want in this industry, pipeline and water leakage. People also ask about oil leakage. I think oil there can be more challenging, since oil and sand have basically the same dielectric constant. Understanding the contrast is more challenging, especially because we cannot just go and leak oil in this amount. So it wouldn't be right. So another trend, and this is really important for the country right now, is using any remote sensing to detect archaeological remains. So the whole area, so preservation and spreading the history of the area is really important to the Emiratis. And UAE has a really rich history that spans over 8,000 years, that include what they call the Neolithic age. So they had settlements there from 10,000 years BCE, Bronze Age, Iron Age, this pre-Islamic, and all these they have spread around the country different kinds of settlements. So you see different kinds of archaeological remains. Also the flight irrigation system. I will talk about this also later. And this maritime heritage in the area in the Gulf, they have many boats under the water. This is also something really interesting. In UNESCO World Heritage Framework, so this area where we mapped the two examples I presented here is in a city called Al Ain City. Al Ain basically means the source of water in Arabic, and is a really important site there. They have all these rich archaeological remains that they are trying to detect or map using SAR, our global SAR. Okay, so this is the importance. So based on that, by September last year, I was approached by an archaeologist from the Department of Culture and Tourism in Abu Dhabi, And they were interested in trying this SAR system in this site called Hilly Archaeological Park. It's one of the parks that UNESCO recognized as a very important site for archaeology in the world. So what we see there on the top right is the top view of the site, and in white, because before we flew there, it was before their excavation season that happens between November and March, where the temperatures are there. And we flew there before this, and the data has been processed recently 2 months ago. But in the meantime, what was interesting, they could give us information because since they excavated, we could get some ground truth. And the idea with this project was not simply go there and prove we could find. Archaeologists, they have this connection with GPRs and satellite SAR, so they understand the challenges. So the idea here is a partnership to see how we can tune the tool in order to use it in a better way for this detection. So this site is particularly challenging because what we see here is basically the site cover. They cover by sand and use these sandbags to mark the locations when they found the remains. But what happened here? All this was built 4,000 years ago, and the constructions were made out of mud bricks. Mud bricks, sand in the region, basically they are the same electromagnetically. What is the difference? The compactation. This is what differs. So it was particularly challenging. And what we did, we flew there. So some more information. And yeah, this is the full view. We flew there and they gave us these ground truths. They could map only the surface and they gave us this shapefile. What we did, we used this shapefile to train a neural network on the surface and try to detect something underground, ranging from surface to 3-4 meters deep. And this was the SAR image set we used, P-band. The trained eyes even from the archaeologists, they could find some interesting features in these images. But what we did here is train the neural network at each 25 centimeters. We had the slices at each 25 centimeters. And what we found inside this fort, because this shapefile showed a fort, we could find other features there that they found really interesting. They are now in the next excavation season start looking for these. For example, one meter deep, we found some remains that could be interesting. 3 and 4. For some cases, like 4, they say, look, for this region, 4, no way. It was maybe something natural, some natural formation. I have this grave on the ground, a block. But everything that comes in a proper structure shape could be a target. And this is what we found applying the neural network. So in red, you see the shapefile, and this was the only information we gave to the neural network. This was also Luca's work. And then we see it goes, and suddenly it breaks. This part here, we see some debris here. Maybe this is just a natural formation. But what they say, that up to meters of depth, we can have, what could be this case here? Could be the walls of this construction that with time broke. Because again, quite similar. In this region here, we have rains. So you see there and there. What is interesting here, the only data we had to train this neural network was the surface, but we can see how the walls goes down and certain point they break. So this is under their investigation now, but according to their eyes, they are experts, they were really excited about what we found. This is one thing. So Lucas was the one responsible for this work, and what he did here, he used deep learning segmentation for detecting surface substructure. We have some advantages here and also limitations. The main one is the lack of ground truth. Okay. But again, the more we work, the more information we get, the more ground truth we collect. So it's a really promising work here. And the good part, this is a collaborative work, so we don't need to show them final results. We're still analyzing all this. The second one is my personal favorite, is the flash. What are flash? Ancient irrigation systems. They are basically tunnels that the people from 3,000 years ago to 2,000 years ago used to build, to excavate, to bring water from one point and distribute to other points. So instead of having pipelines, they had these tunnels. What we see on the top right is basically the fallage going to the surface to distribute water. In other points, you see the shafts that could be used for collecting water along the fallage pipe. We are not just talking about 100 meters, we're talking about kilometers of water of this system. So basically, they are these tunnels, 1.5 to 2 meters of width. And what we see here, this is information I got from the DCT website. They were there digging to maintain, because these are also archaeological remains from previous areas. So we have here information. So the mother well, AIM, so the city is called Al Ain for a reason. So it's passed by several of these canals. And what happened here? In 2023, you have been asked to fly in an area, blindfolded basically, because we are advertising we could detect it underground tunnels. So a client gave us this area and didn't mention much about it. What I could detect there, the shafts, and this was collapsing in many points, as you see there. Fenced, what you see here is the SAR surface image. I think this is feedback surface image from 3 helical flights we carried out there. These bright spots here are the fences, and at the center, you see the shafts. The image is so good that you can count the number of shafts you have there, about 11. So this was done in 2023. By the time we didn't have much computational resources, so Kristen was the one processing these images. We just, to deliver the proof, we could detect tunnels, we just process 50 by 50 by 50. So I won't show you here what we found, but all I know is that the client was impressed by the results. Apparently he knew what was underground. I didn't know by the time this was a fallage, one of the fallages from the flash systems. So what we did now that we have more resources, we reprocessed the data, and this work was done by Eduardo. I believe most of you know Eduardo here. So basically, we reprocessed the 3 helix again, adjusting the DM, etc., a higher sampling rate in the processing images. And again, what you see here is this full area, 200 meters by 60 meters. And what we have here, voice show the region with high reflectivity. In the other side, we have the negative part. And what we see here is holes on the ground. This is the line of the fallage where we count the shafts. This is P-band tomography. This is an L-band tomography, LHH, I believe. Well, this is interesting because indeed we can see that there is this cavity underground. We found this before, but in a smaller area. But I wasn't happy with this because my point here is the following. I walked over this surface and there is no cavities being shown there. So this is the point, because what happens, like in the water map I showed you, everything is being reflected to the surface. And we need to show the client, the scientific community, that certain point, this starts at a certain point and ends at a certain point. So Eduardo has been working on this, and 2 days ago he sent me this, what is really interesting. Here, again, pure P-band tomography, and using a different approach, adjusted DEM. He also applied exponential attenuation threshold for each layer, normalization for each SAR image. He could show me this, and this is interesting because you still see the canal here, around 8 meters of depth, but you also see the shafts. I'm not sure if this is the final image, because now we need to try to understand this, probably send someone underground or sending a camera underground. But it's really interesting. Here I have this small video that shows the whole thing. Yeah, the video is not the best one yet. Yeah, but see, you clearly see the canal. So yeah, now I need to show this to the archaeologists to understand what we have there. 3 minutes. Okay. Finally, the reason I mentioned before, we are working, this is Leonardo's work. When we flew over the area to detect the pipeline or the leakage, this was the scenario we found. João, Jean, and Leonardo had a really hard time to filter all these reflections over the pipeline and over the leakage area. So this was a problem we detected before in a previous work, and Leonardo was cooking a solution for this, and now he presented the first results. That was the following. He's detecting the sources of all these high reflective points and generating all these side lobes that contaminates the area, and applying a filter directly in the raw data. We could eliminate this. So you see here, the left image, the original one, the same normalization. The right one, the image filter. This surface, but what is interesting here, that this goes down. What you filter on the surface, because you are attacking the raw data, it also manifests underground. So this is 2 meters of depth. So this would be really, really helpful. And now we are planning to repeat all the pipeline tests and the leakage tests using this new approach. Because why it is important? Because if you fly over an urban area, you have this information. So with this, I conclude my presentation. The poor Ikeda was drawing numbers here during the presentation. So that's it. Thank you.
Thank you. Thank you. Thank you very much. Questions?
For the presentation, but I have 2 remarks here between the presentation of you and yours. I like a lot the 3D representation of you. We need to learn how it is, because the Ivaboro residences. It was very well plotted.
Yeah.
So we need to get teachers. And the others, for you, this reflection, suppression is amazing. So it's for the range system, you have no headaches more.
I was just thinking that
It's impressive. It's the suppression.
in a desert area, maybe less, but in the UK where you've got a lot of interference from walls, fences, animals, what have you. It's really important that we find ways of filtering out the noise and the other reflections so that we can see what's really there.
Yeah, no, this is a problem. It's happening even there. For example, usually you think, okay, you are in the middle of the desert, you find anything but sand. What's not true. So transmission lines, they interfere, they propagate, they spread energy all over the target area. For pipelines, especially depending on the area, for example, we had a test there, planning to revisit all this data again. The pipeline was running really close to the road. And you don't build the road just putting asphalt over sand. You have rocks, concrete, etc. So all these interferes. So this approach, Leonardo is still working on it, but I think the way it is now, we can already use it. And you're right about the 3D. I was really impressed. And this is something I keep telling the guys, we need to find a way to display this and to convince people, no, it's here, here, here. My problem now is, I think Eduardo was quite hard on the attenuation. It's good, but because I could see all those shafts there, I need to understand if it's that small, etc. And again, the main problem is ground truth. We cannot just, because this is, now we have this partnership with the archaeological department, probably I can go there. When we first flew in that area, basically the guys, they didn't give us any information. Just go there and fly. So we did. And no one was believing on those first results. But now, once we understand what is that, so we have another proposal to fly in another area for this collage. It's my favorite one. It's really interesting. You're right. How to plot this in 3D properly? Really tricky.
I think they
Really beautiful.
they only did a 3D or they prepared the data for taking the threshold.
Yeah, exactly. It's really, really beautiful.
Any other question?
I have a small little question.
Just a second.
You showed nice results about the autonomous side of suppression. So which approach have you used?
Well, Leonardo is removing this information in the range compression compressed data. Apparently, SAR is not my background, but he's using entropy to detect the high reflective points in the raw data and filter them out.
Then congruences, to use the congruences of different images. Okay, then
I cannot tell you this, but Christian maybe can answer because John has been working with him as well. Yeah.
privately,
It's simple.
privately right now.
No, and
I want to delete a lot.
for what I could see, it's really simple. It's really genius.
Still on site low level suppression, I have another question. Do you need some kind of appeal information about illuminating the scene, or it's totally blind and it works?
Initially, when he started, he processed once, but he wants to automatize that. So the idea is to apply entropy to detect where are these high reflective points and doing this automatic. So we won't need in the future to process the first image for these. So right now, I believe he still needs to check We started these in September, so these are quite brand new results.
Could you say something about the exponential attenuation threshold that you talked about in step 4?
Look, Henry, I can't honestly, because this is something that happened in the last 3 days. Yes, he sent me those images. I was quite satisfied with the first one, although understanding that hole wasn't there. But I could see the canal, so that was quite nice. And then he sent me this one yesterday evening. I need to understand exactly what he did there. According to him, something people do for human body scan. I need to check.
Congratulations from the presentation. The last two results are really very impressive. Are you negotiating with these archaeologists for the ground truth, to perform a ground truth activity?
Yes. Now,
So they can perform installations, with careful installations?
no, for the falage.
Yes.
No, for the falage, they don't excavate, otherwise will destroy the archaeological remain. But I believe they might have more information because, for example, talking to this lady, Tatiana, she's an archaeologist from Portugal, working there for several years. What she told me, there are many falage from different eras. So some of them, what they call pre-Islamic, they are not that deep, 5 meters. And then what happened, I don't know, with time, water became more hard to find. They start digging deeper. So the newer the falage, the deeper they are. So I need to present these results because I presented this in a forum for archaeologists recently in Abu Dhabi. They were impressed by the results, but since then we could not talk because several things happening. Next week, I will show this again in a workshop we'll have with them to define the agenda for the next year. So I plan to collect more information. One idea is to send a camera there and see if we can find more information about
Yes,
the
optical fiber
Yeah, exactly, something like that.
cameras.
Or also getting the information they have. Like, I really don't know what kind of information they have.
These shepherds, there's a way to verify that they are really shepherds or not.
Well, when I was in the field, what I did, a simple experiment, just drop a rock and try to measure the time and infer the depth. According to my calculations, it was ranging between 10 and 18 meters. So but again, I need to check because this is in their record. I just knew about these holes were falage last year for the August 24. So, but since then we could not talk properly, but they have the information and they like to share this information and collaborate. So probably soon I will tell you more about this field.
Thank you.
And the last question, let me. Fernanda from TAC.
In fact, it's not a specific question. I would like to see your last slide because I saw many important insights, and I would like to take a picture.
Okay, no problem. Yeah, I'm just trying to summarize the takeaways here. Yeah, oh, this is an important, thank you, because this is probably the most important part here. The collaborations. What I realized doing this, because we are trying to do this by ourselves without using the proper experts for each field. For example, leakage or for these archaeological remains, of course the archaeologists are the best, but not only the archaeologists, the geologists as well. Because they have all this information. For the leakage, for example, I miss knowing more about how sand, they have this very specific environment, how sand absorbs the water. It's different from here. For example, I was in contact also with people that are interested in monitoring the mangroves. And what I've learned, the mangrove in Brazil is different from the mangrove in Middle East, is different from the mangrove in Australia. I cannot take an expert in mangroves from here, there, because it's different. So having these experts in each of these subsurface fields is really, really important. Because we are just the ones mapping the area.
Thank you.
Okay, thank you very much, Luciano. Thank you.